Alright, we're going to talk today about hydrolysis of esters and saponification, which is one of my mostest favouriteest words in chemistry because it just sounds really funny. It means saponification. Who says saponification for crying out loud? It's just hilarious. Right, so hydrolysis of esters. Here we go. Wakey, wakey machine. The hydrolysis of an ester in aqueous solution results in the breaking up of the ester and the formation of an alcohol. You always make the alcohol, and then you'll make either a carboxylic acid or the anion of the carboxylic acid called the carboxylate ion. Depends on the pH of the solution. Okay, I'm going to run through this, but just so you always remember, you'll always break the ester up and you'll always make the alcohol. So if you're ever confused, at least be able to figure out what alcohol is being made if you're breaking up an ester, the hydrolysis of an ester. Okay, so hydrolysis of an acid produces the alcohol and the carboxylic acid. Okay, so adding water and acid in the solution means you'll break this up and you'll make COOH and the OH in the alcohol. Okay, so you add, pretty much break that bond and add the water across it. Okay, so you make from methylpropanoate, you'll make the propanoic acid and methanol. However, if I have hydrolysis in a basic solution, so I have sodium hydroxide, it'll give it'll give the alcohol and the sodium salt of the carboxylic acid. Now, if this was potassium, of course, it would be the potassium salt. Right, so here we go. So again, we've got methylpropanoate and we've got sodium hydroxide. So we're going to make sodium propanoate. So instead of C double bond O OH, I make C double bond O O N A, and then methanol as well. Okay, cool. This is going to be quite specific, and you're going to have to remember how to do this. Right, so now we move on to fats and oils. Now, in your workbooks on page 166, there is a beautiful page on fats and oils, and then a whole pile of really awesome questions on page 167. So, have you ever thought about fats and oils? You probably haven't really. So, fats are typically, we think of them as being from animals, and they are long chain ones, and they are generally solid. And oils are generally, not always, but generally plant-based, and they are liquids. Again, not always. I mean, if you think about coconut oil, it can be a solid or a liquid. Of course, coconut oil is quite trendy these days. But fats and oils, we kind of put them together and call them lipids. Now, lipids is fine, but if we were talking about them from a chemistry point of view, we call them triesters or triglycerides. You might have heard of that word before, but if you check out this one here of the triesters, what has it got in it that we have been looking at? Oh, by crikey, it's got esters. Okay, so these are esters, and how many of them do you think there's going to be? Maybe 3? Cool. So triglycerides, triesters, fats and oils, lipids, all the same thing. So these are made from glycerol. Propan 1,2,3-triol. You should be able to figure out how to draw that, right? Propan, 3 carbons, 1, 2, 3, triol. 3 alcohol groups on 1 carbon, 2 carbon, and 3 carbon. Okay, so we've got glycerol, propan 1,2,3-triol, combined with 3 long chain carboxylic acids. These are called fatty acids. Again, you might have heard of that term before, fatty acids. There's lots of talk in, beauty products and things talking about essential fatty acids and stuff like that. These fatty acids, these long chains, when we say long, we mean long. Like, I mean 16, 20, heaps long chains of carbons together. Okay. The ester link forms between the OH group of the alcohol and the H atom from the carboxylic acid with the elimination of water. Glycerol is an example of a triol, has 3 OH groups present. Each of these can form an ester link, each of them with a different carboxylic acid, for example, the fat called stearin or stearic acid. Oh, what's happened to my little... It's gone. Why have you decided not to start working? So here we can see we've got glycerol, the 1,2,3 propane, propane 1,2,3 triol, and 3 different fatty acids. So these are R1, R2, and R3. Now remembering R can be like 20 carbons long. In the case of stearic acid, it is 18 carbons long. 18 carbons long, right? So you can see this OH will react with this group over here, and this will add it on to this as an ester linkage. Look, CO, C double bond O, R1, CO, C double bond O, R2. So 3 ester linkages and 3 waters. Okay, so that is, this here is what we call a fat or an oil. Okay, here we go. So saponification, soap making, where you have the 3 ester linkages broken down, hydrolyzed by heating with sodium hydroxide, so basic solution. This releases the original glycerol molecule plus the sodium salts of the long chain fatty acids, which are the soaps. This saponification process is shown next. Here we go. Alright, so here is our fat or our oil, okay, and it is mixed with sodium hydroxide solution. Okay, I make glycerol, the propane 1,2,3 triol again, and then I make these things here, which, remembering this R chain is huge. I'm going to draw one for you. Here we go. So I'm going to draw it the shorthand cheating chemistry way. Yep, so I've got 1 carbon, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So this carbon here has a double bond O. Let's put a carbon in just so you see it. Carbon bond O, single bond O minus, Na plus. Sodium salt of this huge big long fatty acid. Now I have drawn it very deliberately like this because I'm going to tell you the secret of how soaps work. So this here is a soap. Cool? Alright, if you ever wondered how soap actually works, how does soap manage to get rid of, you know, greasy, nasty stuff off things? Okay, so this is my soapy molecule. Now if you think about this end down here, do you think it's going to be polar or non-polar? You're right, this end here is non-polar because these are carbons and hydrogens just all in a chain, right? It's non-polar end. Now this stuff here, is this going to dissolve? Is it going to dissolve in water? Or is it going to dissolve in oily, greasy stuff? Yeah, it's going to dissolve in oily, greasy stuff, not in water, because water is polar. However, this end here, do you think this end is polar or non-polar? It's polar, and this means this end here will dissolve in water. So when I draw soap molecules, I tend to draw them like this, right? And this end here is the positive end, and this end here is nothing. Okay, well, just, yeah, do that anyway. So this end will dissolve in water, and this end will not. So if I have, say, I'm really bad at drawing this, and I try every year to draw it, but it doesn't work very well. Say I have a nice little plate here. Here is my plate. Alright, and on my plate I have some horrible, nasty, greasy stain. Alright, I go and I put this into my sink, and in my sink, in the water, right, in the water I have some soap, and this soap has the bits that look like this, okay, and this end is charged and this end is non-polar. Okay, so this bit dissolves in the water, woo, and this bit doesn't like it very much. This is hydrophobic. I forgot to tell you those cool words. How silly am I? Hydrophobic. And this end is hydrophilic. Philic meaning it loves it, phobic meaning it hates it. If you have a phobia, you don't like things. Okay, so what happens here is that all the taily bits surround all of the greasy nastiness, alright, but the heads dissolve in the water. So what you end up with is these globular bits of fat that you can't see because they're so tiny in the water, surrounded by all these soap molecules, which means that this bit dissolves in water. It's so clever. Always gets me excited when I talk about saponification. Alright, cool. But things you need to remember is the fact that fats and oils are triesters, okay, and you can break those up using a basic solution to make glycerol and 3 moles of soap. That's us. Hope you enjoyed it.